Hey guys, it's Zach with Aldeck, and welcome to this ALINT-PRO tutorial. Today we're going to use features in ALINT-PRO to explore finite state machines. Finite state machines, or FSM for short, are present in all major designs and components within those designs. Despite them being common, the number of mistakes found in FSM implementations is surprisingly huge. While some coverage tools can discover some advanced errors through simulation or formal checking, ALINT-PRO can catch many errors through quick static analysis. We're going to use an example FSM design in ALINT-PRO. In the top level file, we can see the signals relevant to the FSM, such as input and output, as well as the FSM declaration which declares states from S0 to S14. We can also see an internal signal, count, is declared that is 3 bits. Then we can see the actual operation of the FSM, which shows transition logic from state to state and conditions of each state transition. We can also see the use of the internal count signal. At the bottom, we have our FSM output signal assignments. Now that we're a bit acquainted with the code, we can go ahead and run the project. Once the tool finishes its run, we'll be able to see in the console that the run was a success. First, we'll open up the FSM list viewer, which can be accessed in the toolbar via FSM viewer. If we expand the project, we can see the different modules within the project, but we have just one, FSM. So if we expand FSM, we can see all the finite state machines within that module. Again, we have just one in this module. We can expand that FSM to see the input signals, internal signals, output signals, states, and transitions. We can also see in the value condition column that it has identified the FSM as a Moore machine. It also indicates the states to be encoded in binary. We can expand to see the exact encoding for each state. The output signals are identified as Moore because their output are determined only by the current state and not by input. Now expanding the transitions, we'll be able to see all the defined transitions from inside the FSM. Expanding each transition, we'll be able to see the condition that will allow that transition to take place. So if you look at S2 to S3, we can see its condition will be when write is logical high. For transition S2 to S4, we see it indicated as none. If we double click on this transition, it will cross probe to the HDL editor to show it in code, and we can get a closer look. We'll see that the transition S2 to S4 takes place in an else statement without a condition. You might also find a condition to be none when the transition occurs by default. So for instance, from S0 to S1, the transition occurs without any condition. And if we look at S10 to S11 state transition, we'll see the condition indicated by left or right being logical high, and can cross probe to the HDL editor to verify this is the condition. From here, it will be helpful to look at the FSM graph. We can right-click on the FSM in the FSM viewer and cross-probe to the graph by Show in Graph. From a first look at the FSM graph, we can see in the toolbar some basic zoom controls, such as zoom in and out, and we can also be done using the left mouse button and dragging in different directions. Up is zoom out, left is zoom to fit, and right and down is zoom in. Similarly to the FSM viewer, you can cross-probe from the graph to the HDL editor. You can cross-probe from the transitions, represented by the arrows, or from the states, represented by the circles inside the graph. When a state is blue, it indicates our initial state. When it is red, it indicates a dead state. When it's gray, it indicates unreachable. And the white state off to the side indicates a redundant state. The initial state is denoted in code and is usually the default state after a reset. A dead state is caused when the FSM enters a state that can't be exited. An unreachable state is caused when a transition condition is unable to be met. When this occurs, the transition to the unreachable state is considered to be broken, and it is marked with a red X. A state is considered redundant when it plays no part in the FSM. There are no transitions to or from the state, therefore it is redundant and unnecessary. Seeing these issues visibly is helpful, but it is nice to have a list of violations to outline the issues with the FSM. If we open up the violation viewer in the toolbar, we'll be able to see what issues ALINT-PRO found with the FSM. We'll also want to have the rule description viewer open to help explain each violation we find in the design. Here in the violation viewer, we are able to confirm the issues with the FSM that we found visually with policy violations. We can see the violation with the description and location of said violation. In the violation viewer, there are 4 violations shown, which describes a redundant state violation, deadlock state violation, the unreachable state violation, and live lock violation. The unfamiliar violation here is live lock. We want to see where this live log violation is occurring in our FSM, so we can cross-probe from the violations viewer to the FSM graph by right-clicking on the violation and going to Show in FSM Graph. We can see in the FSM graph that transitions between S8 and S9 forces the FSM to enter a loop it can't exit from unless the design is reset. ALINT-PRO is able to recognize this and reveal it as a policy violation, even though it may not be visually obvious from the graph. This is why we want to check our violations. To make sure this is not missed, we can take a screenshot of the highlighted violation in the FSM graph using the screenshot button in the toolbar, and we'll name it vlog4044 for the policy violation. There are a few extra things we can look at pertaining to the FSM analysis tools available in ALINT-PRO. We can pull up a full FSM text report on our design by going to the Flow Manager and opening FSM Report. This will contain information about your design as a whole, such as how many FSMs there are, which modules they are in, and the information specific to each FSM. It will show what type of FSM it is, its encoding, and other facts about the FSM. It will show the state values and state transitions tables, which indicate each state's encoding and transition conditions. Here at the bottom of the report, we have our FSM structure, which goes through the different processes found in the FSM and identifies their location and node type. Now we should look at the FSM policies. If we go to the properties of the design and the policies subsection of linting, we can see the policies used for the FSM coverage. In the ALINT Premium Rules library, we have the FSM descriptions policies, which provides rules to check your FSM designs against. In case you wanted to disable some policies, that is also possible. The ALINT Premium and Stark policy available in ALINT-PRO libraries should provide solid coverage for designs and should satisfy most customers' linting needs. It is important, however, to make it clear that the linter can detect limited cases of dead or unreachable states and need to be caused by the FSM unit itself. More advanced dead or unreachable states are possible through external conditions, such as a transition that is dependent upon an input signal that is never activated. Because of this, simulation and formal checks for your designs are necessary, especially for safety-critical designs. Well, that's it for this tutorial on FSM exploration in ALINT-PRO. Thanks for watching.